Evolution doesn't just adapt. Sometimes it experiments. Take this head, long, needle-sharp. You'd expect a fast, deadly predator, but evolution had other plans. This is Hupehsuchus. Imagine an armored potato, sealed inside a rigid shell. Its ribs and belly bones overlapped in opposite directions, forming a solid bony tube, a body so locked it couldn't even wiggle. And that creates a serious problem. If your chest can't expand, how do you breathe? Most animals pull air by expanding their ribs, but Hupehsuchus was trapped in a permanent corset. So it evolved a different solution, a hepatic piston. Muscles pulled its liver and internal organs backward, like a biological pump, drawing air into its lungs from the inside. Not fast, not flexible, but it worked. And here's where evolution gets even stranger. That sharp, streamlined look, you'll see it again, but in a completely different animal. Meet Xinpusaurus, a thalattosaur with a tail up to twice its body length. It looks built for speed, almost like a swordfish, but it wasn't slashing through prey. It was digging, using its snout like a shovel to root through the seafloor. Same shapes, completely different jobs. That's a pattern. Evolution doesn't design from scratch. It reuses, reshapes, and repurposes. Even scientists are still figuring it out. In 2023, Hupehsuchus was thought to be an early mini whale, filter feeding like modern baleen whales. But newer models showed it didn't have the energy to survive that way. Not a whale prototype, just another evolutionary experiment. And one more thing, none of these are dinosaurs. Dinosaurs ruled the land. These are marine reptiles, diapsids that took over the oceans after Earth's biggest extinction. Different lineages, different solutions, and somehow these strangest designs survived. If you think you have to travel the whole planet to find history's weirdest creatures, think again. Hupehsuchians were such extreme homebodies that their entire evolutionary history, spanning only a few million years, took place exclusively in 2 small counties in China's Hubei province. They basically had no passports and zero interest in migrating. They remain one of the most geographically restricted groups of marine reptiles in the Triassic. But why do we call them underwater tanks? In recent years, high-resolution digital scans finally gave us the answer. While most marine animals undulate their bodies like eels to swim, some Hupehsuchians, like Hupehsuchus, had a literal bony tube surrounding their torso. Their bored ribs were locked together like a jigsaw puzzle to create a completely rigid cylinder. This means their waists were efficiently deadbolted. If this guy wanted to look behind him, he had to turn his entire heavy body around. He was a true armored potato that evolution seemingly forgot to give a spine that could actually bend. So how does a rigid tank swim? Scientific rotoscoping analysis in recent years showed that when your body is as stiff as a log, your tail has to do 100% of the work. They used rapid oscillations of their powerful tails, much like modern crocodiles, to propel their heavy mass forward. Then there's their most bizarre invention, polydactyly. While most vertebrates were happy with 5 fingers Hupehsuchians, like Hupehsuchus, invented extra digits to create wider, fan-shaped paddles. These weren't for speed. They acted like the rattle fins of a tank, used purely for steering and maintaining balance near the shallow seafloors. And remember, these creatures were not fish, no gills. Every breath meant hauling that armored body up to the surface like a tank was struggling for air. And what about lunch? Remember that 2023 claim that they filter fed like whales? Newer biological reports completely shut that down. Their long toothless snouts didn't have space for baleen or any kind of filtering system. But they weren't simple vacuums either. Their upper jaws weren't fully fused, creating what scientists call an intercrural space. And the front of their jaw could flex and spread apart. Think less vacuum, more pelican. Their mouths could expand outwards, gulping soft prey in bulk. Small fish, invertebrates, anything easy to scoop up from the seafloor. A flexible, expandable trap attached to a completely rigid body. Evolution doesn't balance things, it just makes them work. Unfortunately, this extreme specialization became their weakness. They were so optimized for one environment, shallow, calm waters in one tiny region, that when conditions changed, they had nowhere to go. No flexibility, no migration, no backup plan. An evolutionary dead end. Now let's look at their flexible, globe-trotting rivals, the thalattosaurs. At first glance, Xinpusaurus looks like a precision weapon. Scientists put that idea to the test using finite element analysis, basically a digital stress test. They simulated what would happen if it tried to slash prey side to side. And the result? Catastrophic failure. The snout would snap under torsional stress. But when used differently, pushing straight down into the seafloor, it stayed stable, calm, strong, and efficient, like a shovel built to dig, not slash. Remember how we said Hupehsuchians were homebodies who never left China? Well, the thalattosaurus were the exact opposite. These sea lizards were the true world travelers of the Triassic. Their fossils have been uncovered from the mountains of Alaska and coasts of California to the heart of Europe and southern China. Think of thalattosaurs as marine iguanas on steroids. Unlike their rigid, armored rivals, they had incredibly flexible, eel-like bodies. But here's the kicker. They kept the powerful claws of their land-dwelling ancestors. This means they were likely amphibious, crawling onto rocks to rest or sunbathe, just like modern iguanas. And then there's that endless tail. A thalattosaur's tail could be up to twice the length of its entire torso. Talk about having different zip codes. If a thalattosaur threw a party at the tip of its tail, the head wouldn't get the invitation for 2 days. This whip-like tail was their engine, driving them through the water with smooth, snake-like motion. When it came to snouts, evolution gave them a full toolbox. Take Xinpusaurus, about 1.5 meters long. It looks like a scaled-down swordfish, perfectly mimicking the shape. But it didn't use that snout to slash. It used it to dig, plowing through the seafloors like a biological shovel to uncover soft prey. And then there's one of their most advanced features, their eyes. Inside the eye socket sat a sclerotic ring, a structure of interlocking bones. Think of it as built-in diving goggles. But these weren't for protection. Their shape had something called aperture eccentricity, a design that helped prevent the eyeball from collapsing under pressure during deep dives. In other words, their vision system was pressure-proof, and it gets even better. These adaptations suggest they were cathamerals. No fixed schedule, no bedtime, just as active at midnight as they were at noon, hunting in bright coastal waters or in the dim, cold twiling zone of the ocean. Always on, always watching. And despite that long, exaggerated body, they weren't clumsy. Recent rotoscoping models show they were highly optimized swimmers. By controlling the frequency of their tail motion, they could unleash sudden bursts of speed, perfect for ambushing prey or escaping something bigger. Even in the bizarre world of marine reptiles, not all adaptation work in the end. Take specimen XNGM WS50R4, a 4.8-meter predator that once ruled the waters. Inside its body, paleontologists found something that shouldn't have been there. A 4-meter Xinpusaurus, nearly whole. This wasn't a casual meal. No, this was an attempt at swallowing a meal far too large. Evidence points to a grip and tear strategy, a quick, aggressive move to disable the Xinpusaurus' tail. But then, something went wrong. The predator learned the hard way. Don't bite off more than you can chew. The prey was just too big, too rigid for the predator, and it couldn't even finish what it started. It choked, unable to swallow its meal, and died soon after the attempt. This moment was a failure of adaptation, a predator miscalculating the size of its prey and meeting the consequences of its overconfidence. In the unforgiving world of the Triassic Ocean, even the mightiest can fall prey to their own designs. And now, we turn to a more microscopic perspective. If you want to truly understand how these creatures lived and died, we don't just rely on fossils, we follow the receipts. Every detective knows if you want to understand the suspect, you follow the receipts. We can't check bank accounts, so we check isotopes. By analyzing chemical signatures locked inside teeth and bones, scientists reconstructed their diets, who ate what, where they hunted, even how deep they dove. The Triassic Ocean leaves a paper trail written in chemistry, and that trail leads us to something even more extraordinary: ancient proteins. Preserved collagen, still intact after over 250 million years. Using a technique called Van Gissen's staining, these proteins light up bright red under the microscope. Not rock or mineral, original biological material, still here, still identifiable. This is the molecular fingerprint. The smoking gun. It confirms exactly where these animals belonged on the tree of life. Not dinosaurs, not just generic lizards, but a unique lineage of marine reptiles, engineered by evolution to dominate a world that no longer exists. Now, it's time to ask, where do these creatures actually fit into history? According to phylogenetic charts finalized in recent years, we're looking at a serious family separation. Dinosaurs belonged to Archosauria, the same group that gave us birds and crocodiles. But Hupehsuchus and thalattosaurus went their own way, straight into the sea, like distant cousins who never showed up to the family reunion. In terms of size, a modern diver swimming alongside a thalattosaurus would be in for a shock. At around 4 meters long, this creature was massive, but the real nightmares, the proportions. A small, lizard-like torso, followed by an endless whip-like tail that just keeps going. In contrast, Hupehsuchus were much smaller, usually under 1 meter, think Labrador-sized, but armored like a tank and unable to bend. So why did these innovators disappear? This is more than just extinction. It's an evolutionary shutdown. Specialists versus generalists. Thalattosaurus tried to do everything. They could swim, but not like true ocean predators. They could move on land, but not efficiently. They lived between two worlds and mastered neither. Meanwhile, their rivals made a different choice. The ichthyosaurs abandoned land completely. Their breakthrough was to give birth underwater. And even that had a learning curve. Early ichthyosaurs gave birth headfirst, a leftover trait from their own land ancestors, which created a deadly problem. Newborns risked drowning during birth. So, evolution corrected it. Later species gave birth tail first, keeping the baby's head inside the mother until the final moment. A perfect aquatic solution. They became some of the fastest, most efficient predators of their time. But the real advantage was invisible. Their metabolic engine. Ichthyosaurs were homeothermic endotherms, warm-blooded, running hot between 31 to 41 degrees Celsius. Constant energy, constant speed, constant control. Day or night, shallow or deep. They were always on. Thalattosaurs? They couldn't keep up. They were poikilothermic, stuck in a cold-blooded middle ground. Slower metabolism, less endurance, less power. In a world that was getting faster, they stayed limited. And in evolution, that gap is everything. As ecosystems became more competitive, specialization won. The ichthyosaurs didn't just survive, they dominated. And the thalattosaurs, they weren't weak. They were outpaced and outperformed. They weren't bad at surviving. They failed because something else became better.